Okay, I'd like to tell you about magnetic flux. Turns out that every field that we've studied has a flux attached to it. So gravitation, here are the three fields we've studied: the gravitational field, the electric field, and the magnetic field. They each have a flux attached to them. So flux we give the symbol phi to, and so this would be phi sub g for the gravitational flux. This would be phi sub e for the electric flux, and phi sub b for the magnetic flux. But do you see how similar the formulas are? Each one is just the field. It's the integral of the field dot dA. Okay, that's a dot product. And so let's take a look at the flux through a surface. That's what you're really calculating, is the flux through a surface. So here are three different surfaces. Let's say that they have the same area, but they're oriented in different ways. So let's put a field here. It doesn't matter what the field is. It could be an electric field, a magnetic field, or a gravitational field. But let's just say right now that this is a magnetic field. So if I wanted to find the flux through each of these, then it turns out that the dA is just a little area. So we're doing the magnetic flux. So it's going to be the B at the surface. So B on the surface dot dA. Now the dot product says that you have to take the part of B that's parallel to dA. So let me show you a little dA. A little dA right here is this little segment. It's infinitesimally small, and it's going to be, I'm going to point it this way. It could be pointed that way as well, but I'm going to just point it the same way as the field. And if this is the B field right here, and let's say it's uniform, so the lines aren't spreading out and they're not getting any closer together, then when I do the integral of B dot dA to get the magnetic flux through there, when I do that, the first thing I can do is, you see how for every single dA, the B is in the same direction? So the first thing I can do is I can get rid of that dot product. So it just turns into B times A, and that's because B is parallel to dA at each point on surface. Okay, so that's the magnetic flux. And now you see how the B doesn't change no matter where you go? So you can pull that B out of the integral. I didn't leave myself some space to tell you the argument, so I'll just tell you it orally. And that is that B can be pulled out because B is the same at every spot. For every dA, the B is the same value, so you can pull it out of the integral. So now you're left with just summing up all the dAs, and so that's just going to be B times A. So in its most simple form, the flux is just going to be a B, the intensity of the B field, times the area of the thing. Two things have to be the case for that to be true. You have to have the B always in the same direction as the dA, and the B must be uniform throughout the whole surface. Okay, well that's not the case for this surface. This surface, the dA, if I drew a little dA, it's pointing that way, let's say. Again, we could say it's pointing upward too, but I'm going to say it's pointing downward. And you know, I'm making these dAs are infinitesimally small, but I'm making them so that you can see them. The vector would really be really tiny because it's infinitesimally small. But do you see how the B is this way and the dA is that way? So you only want the part of, if this is theta, you only want the angle between them. You only want the part of B that's in the direction of dA. Or you could find the part of dA that's in the direction of B. Doesn't matter. And so that's going to involve a cosine. And so you don't have as much flux going through here. In fact, you have no flux going through this one because the dA is straight up. And the B is this way. And so how much of B is parallel to dA? None. And so the dot product would have you make that be equal to 0. There's no magnetic flux going through there. A couple more things about magnetic flux. You can think of magnetic flux as the arrows that go through the surface. So the more arrows that go through the surface, the more, or I sometimes will say it's the sunshine going through a window. So if you think of the field as being sunshine, and this is a window, this window gets the most sunshine. It's got the most lines going through it. This has less flux. This has less sunshine. This has no sunshine going through it. There is no flux going through here. Okay, what are the units for flux? B times A, so the units would be Teslas times square meters. And that has a name. We sometimes call that Teslas times square meters. We call it the Weber, after a German scientist. Okay, so that's how you calculate flux for any field. Okay. Now, it turns out then that the reason why flux is important is because of a guy named Gauss. Actually, he's the one who created the idea. And so it turns out that if we talk about closed surfaces, let's talk about closed surfaces for a second. Here's a closed surface. Now, a closed surface is one that's three-dimensional that closes in on itself. So it's not like a cup, but like a cup that's covered. And so like a sphere would be a closed surface. And now the direction of dA, I was saying that it could be one of two ways before. The direction of dA is always normally or perpendicularly outward. So that there's only one way dA can go. Excuse me. Again, I am definitely making the dAs too big. They're infinitesimally small, but you get the idea. All right, so that's these are all the dAs. They're normally outward. And so it turns out that here are the laws of Gauss's law for each, for gravity, electrostatics, and magnetism. For gravity, the total flux, this is the total flux through a closed surface. That circle over there means a closed surface, so one like a sphere. The total flux has only to do with 4 times, it's this quantity, it's negative 4 pi, capital G, the universal gravitational constant, times the mass enclosed by the Gaussian surface. So the only thing that matters is the mass enclosed. And this G is on the Gaussian surface, and these dAs make up the Gaussian surface. With electrostatics, the total electric flux, meaning the flux at the Gaussian surface, and the dA is making up the Gaussian surface, that only depends on the Q enclosed by the Gaussian surface divided by just the permittivity of free space, a constant. Same thing with magnetism then. Magnetism, the total magnetic field enclosed by a Gaussian surface, if we're counting the strength of the magnetic field on the Gaussian surface, and these dAs make up the Gaussian surface, they always will equal 0. And let's see why. Well, first of all, notice that we count arrows going into a surface. Let me send an arrow straight through here. That's a magnetic field, let's say. And you see how this is giving us a positive flux through this little dA. But on this side, this one is going to give us a negative flux because the dA is this way, and the B is this way. And so when that's the case, then you got the angle between B and dA as being 180 degrees, which is going to be equal to 0, or that's going to be equal to -1 rather. Okay, I am going to have to give you a small amount on this same topic on the next video. Sorry, bye.